So let's go back to harmonic oscillators. And remember we had two types of simple harmonic oscillators. We had vertical system where gravity didn't affect it except it just made the spring a little bit longer, so you stretched it out and then it just oscillated. You didn't have to worry about gravity, it was just a constant. Or we had a frictionless surface, horizontal, so then the only force was the spring, the gravity and normal force cancel out if you know physics. Otherwise don't worry about it. Now we're going to talk about when we have damping. So damping is just some external force, and it's going to be proportional to the velocity. So here was our undamped differential equation. We're now going to make the oscillations smaller, or maybe stop them entirely somehow. So damping is always going to oppose the motion. So minus some constant gamma times y prime. Damping can probably actually come from friction. So if you just made this friction, then it would go slower and eventually stop, or maybe not oscillate at all. Maybe it would just go once. Or you can install some sort of hydraulic device. So if we could and there's times when you do want damped oscillation, not just regular oscillation in engineering. So they'll install some hydraulic piston in addition to the spring, and then we get damped motion. And it's always going to oppose the motion. So when it's going this way, the spring is pushing this way, and the piston is also pushing this way. And then when it's on the other side, the spring is pulling, the piston is also pulling. So there's our damping term. So now what do we have? Well, m, k, and gamma are all constants. So we have a second order homogeneous differential equation with constant coefficients, plus ky equals 0. So we can get the characteristic equation is going to be mr squared plus gamma r plus k equals 0. And then we can solve for r. It's going to be a little bit ugly. So we're going to get negative gamma plus or minus the root of gamma squared minus 4mk over 2m. And arguable whether this is better or not, but we're going to change the format. So we're going to split up the fraction. So we get negative gamma over 2m plus or minus the root of this thing over 2m, not in the root. Or we could put it inside the root and make it 4m squared. Let's take a couple steps to do this so we see where it comes from. 4mk. It's going to go inside the root and be 4m squared. M is greater than 0, so the root of 4m squared is 2m. No need to worry about absolute value or anything. Negative gamma over 2m plus or minus, and then we can split up this fraction as well. So we get gamma over 2m quantity squared. That's the same thing as gamma squared over 4m squared. And then minus, the 4's will cancel, and we get k over m. And the thing we like about this is there's a k over m term. So is this better than this? I don't know. But this one does have a k over m term, which remember omega naught was the root of k over m before. So it looks a little bit more similar to what we had before. All right. So then what are the possibilities? Well, remember the solutions to this look really different depending on whether we had distinct real roots, repeated real roots, or complex roots. So we're going to look at the three cases separately. The complex roots is the easiest one. We call this underdamped, and this solution is actually going to look the most similar to what we had before. We'll still have oscillations. Repeated roots are going to be called the critically damped situation, and then distinct real roots will be called overdamped. So we'll look at these in reverse order in the next few videos.